In this second module of Chapter 6 on stage models, Module 6.2, I will discuss stage-based models for modular organisms with a specific focus on plants. The first step when building a stage-structured model is to determine how to divide the population into stages that reflect the most important factors that the demography of the species depends on. Body size strongly impacts survival and reproduction of individuals, and discrete size classes are often used in stage-based models. If survival and reproduction have nothing to do with size, for example with a bird species, the stages might be juveniles, non-breeding adults, and breeding adults, or for an insect it may be developmental stages such as egg, larva, pupa, and adult. The life cycle of a species, for example modularity, will influence model structure. Budding hydra, fragmenting corals, and clonal plants are examples of species that can divide into modular, independent units. This modular structure provides opportunities to apply the tools of demography at multiple levels of organization, and the plasticity of this modular structure can lead to individuals shrinking, such as that age and size may have independent effects on mortality. These effects, as well as the importance of dormancy, are considered in the models here. Three idealized models are presented here with variation in life cycles and critical demographic processes. These models here are referred to as plant models, but many aspects of the structure of these stage models could be applied to some animal species. Stage is size for these models, which for plants may be quantified depending on the species as the number of leaves, size of rosettes, or the diameter at breast height. Each of these three models builds on the next and adds additional traits including shrinkage, dormancy, and dispersal among populations. Model 1, growth and renewal. This first model shows growth and renewal and includes four stages: seed, juvenile, small reproductive, and large reproductive. The corresponding matrix elements for the transitions between each of these stages are given here. At the seed stage, individuals either transition into the adult stage with a probability of 0.8 or they die. In other words, there is no dormancy. The input into this seed class is provided through either of the two reproductive classes, the small reproductive or the large reproductive. Individuals in the juvenile non-reproductive class can either transition to the small flowering stage with probability 0.7, or they can remain as non-reproductive juveniles with probability of 0.2. For many plant species, this transition to flowering is size dependent, but for other species this transition is environment dependent, in which case there would be no individuals remaining in the juvenile class if all individuals experience the same environment. From the juvenile class, this model specifies two reproductive classes, and small reproductive individuals have a 0.3 probability of transitioning into the large reproductive class, and the large reproductive class individuals have a 0.5 probability of remaining in this large reproductive class. The life cycle pictured in Model 1 could apply to many animal species that lay eggs and experience a juvenile non-reproductive stage. Most animals, however, show determinate growth and thus have minimal or no growth after the age of first reproduction. Thus, there will only be one reproductive class, with some probability of remaining in that reproductive class if individuals can reproduce more than once. With the values specified in this matrix for Model 1, the growth rate of this population is 2.18, and the stable stage distribution is 63.7, 25.7, 9.1, and 1.6% for the seed, juvenile, small reproductive, and large reproductive classes respectively. Model 2, growth, shrinkage, and dormancy. Modular organisms such as plants can shrink in size, and this may impact their survival or reproduction. Dormancy, a period in an organism's life cycle when growth, development, or physical activity are temporarily stopped, can also influence demography because a population will consist of two parts: the growing individuals that can reproduce and the dormant individuals that can persist for many, and in rare cases, hundreds of years. Here we will consider plant seed dormancy and note that the number of seeds in the seed bank is a function of the seed rain, the fraction that germinate each year, and the fraction of seeds that decay and never germinate. Building on the basic parameters of Model 1, the juvenile class in Model 2 is now divided into a small non-reproductive and a large non-reproductive class, where small and large again delineate a measure of plant size. Transitions include the survival of one stage to the next, shown here. The self-loops where they remain in each of the respective stages. In the reproduction for both the small and the large reproductive classes, the regression including between both adjacent and non-adjacent stages. There are a number of new transitions in this model that reflect two plant traits of seed dormancy and shrinkage. In other words, stasis, or regression between states. All stage classes now show some stasis, in other words, some probability of individuals staying in the same state. The probability of remaining within a state are along the diagonal of the matrix. It should be noted that these stasis transitions represent individuals that stay in the same state and remain the same size. Regression of individuals into prior states may occur through transitions from reproductive to non-reproductive states and also as plants shrink to a smaller size class. The basic structure of Model 2 could also be applied to a species that, instead of shrinkage, shows fragmentation, where larger individuals break apart to form smaller clones of itself. Fragmentation may occur not only for some plant species, where modules break off and become physiologically independent, but also for corals or other modular animals. With the values specified in Model 2, the growth rate lambda of this population is 3.15, and the stable stage distribution is 73.0, 3.2, 19.3, 1.3, and 3.3% for each of these stage classes respectively. Model 3, connecting populations. As an extension to the population projection models for plants considered here, we will consider movement among populations due to seed dispersal, although plant gene flow can also occur through pollen dispersal. In Model 3, each subpopulation has the same transition probabilities as in Model 1, with the added dispersal of seed between these subpopulations. With this structure of connected populations, it is possible to consider either the dynamics of the changes in the number of populations with time, or the population growth rate for the whole population matrix. Understanding the impact of dispersal dynamics on population growth rates is particularly important for conservation questions in fragmented habitats. In the example here, lambda equal 2.3. This ends Module 6.2. In the next module, I will build on these same stage-based matrix model concepts as applied to vertebrate populations.